Okay, chapter 24 is on magnetism, and who doesn't love playing with magnets? Okay, so the term magnetism comes from the name Magnesia, a place on the east coast of Greece where they found lodestones more than 2,000 years ago. These are rocks that you find that have this weird tendency to attract iron filings. They can be used in compasses, and these were used long ago by the Chinese for navigation. So we know that if you have two charged particles separated by some distance, there's an electric force between them. But what you may not know is that if one or more of these charges are moving, you also get a magnetic force between them. This is all part of the theory of electromagnetism. But the electric force and the magnetic force are two different forces in physics, and they both exist together if you have charged particles that are moving. So a magnet, like a lodestone for example, must have moving charges within it. In fact, billions of little tiny moving charges going in circular paths that give rise to this magnetic force. When that happens, we say that one end is North Pole and the other end is a South Pole, N and S. These are called the magnetic poles, and every magnet has both of these. So if you've ever played with magnets, you know that sometimes they repel, sometimes they attract. And the rule is that if you have the N pole facing the S pole of two different magnets, then opposite poles attract. So these will be pulled towards one another. If you have the S facing the S, you get a repulsive force. If you have the N facing the N, you get a repulsive force. And magnets always have two poles. There's no such thing as a single magnetic monopole. So a bar magnet has poles at either end. If you have a horseshoe magnet like this, in a U shape, you have one N side and an S side as well. And the magnetic fields is just this region of magnetic influence surrounding the magnetic poles. And by convention, we say the direction of the magnetic fields away from the north poles and then towards the south poles of bar magnets. And the strength of the magnetic field lines is stronger where the lines are closer together and weaker where the lines are further apart. So electrons in orbits can produce magnetic fields, also just electrons spinning. And in iron, the main contributor to the magnetic field is actually electron spins. So in most materials you have electron spins canceling each other out in pairs of up spins and down spins, but in iron you can have unpaired electron spins that give rise to sort of a net magnetic field. And so neighboring iron atoms do tend to align their unpaired electron spins so that big regions of iron will all have all their spins in the same direction. That's called magnetic domain. But a piece of iron has lots of different domains, each with some random direction of the magnetic field. So a permanent magnet is when you somehow align these magnetic domains, either by placing them in a strong magnetic field or by stroking the iron somehow to align the domains and make a magnet. So here's some unmagnetized iron. All the domains are in random directions. If they start to align a little bit more towards the right than towards the left, then you get an N pole on the right and an S pole on the left. And the more they're aligned, the stronger the magnet. And if you cut a magnet in half, you end up with two magnets, each with two poles. So in a permanent magnet, the domains are aligned no matter if there's an external magnetic field or not, like this bug magnet. In a temporary magnet, like the fridge, it's not a magnet unless it's placed in an external magnetic field. And then, if this is an S pole facing the fridge, then the refrigerator makes an N pole that faces it, and there's an attractive force, which is why fridge magnets always stick to the fridge. They never repel the fridge, because the fridge is a temporary magnet. A compass is a small, permanent bar magnet that is free to rotate about a vertical axis. So the needle, okay, the pointy side of a compass, is the end side of that bar magnet. And that will point away from the end side of any other permanent magnet. And that shows the direction of the magnetic field. If you have a current running down through a wire and you surround it with compasses, you'll notice that when the current is running down, all these little compasses point clockwise around the current. If you reverse the current direction, then all the compasses reverse their direction as well. So the electric current is creating a magnetic field. And you can see these magnetic fields if you sprinkle iron filings around current-carrying wires. So if you have a current-carrying coil of wire or a spiral of wire, that's called an electromagnet. It makes a very strong magnetic field. This magnetic field strength is increased by the amount of current, the number of turns in the coil, and it can also be increased by putting a piece of iron within the coil. The magnetic domains in the iron core will then align with the magnetic field that you produce with the electromagnet and increase the strength. And that's what they use in this junkyard electromagnet. They can turn on the magnet and there's iron in there, and so it can pick up pieces of metal. Electromagnets can also be used to levitate trains. You have electromagnets in the track of this in the train tracks here, and then you have permanent magnets in the train, and the coils are meant to repel and then pull, and so can not only lift the train but can also propel it along. And you can also have superconducting electromagnets that can produce very strong magnetic fields and do it economically because there's no heat losses due to resistance in the wires. So an electric current in an external magnetic field will feel a force. That's also called the magnetic force. And it's perpendicular both to the magnetic field, which in this case is from N to S, and to the charged particle velocity, which is, I guess, along this current-carrying wire. So it would be maybe up or down, I think, in this case. So electric current moves through a magnetic field. It experiences this deflecting force which is perpendicular to both the magnetic field and to the current. And the force is strongest when the current is perpendicular to the magnetic field lines. So here's the current. There's perpendicular to that is the magnetic field, and perpendicular to that is the force, either up or down, depending on the direction of the current. A galvanometer is a current indicating device which determines the current in a wire by measuring the magnetic force that's due to a permanent magnet. This is called an ammeter because it measures amps. You can also take this same thing, hook it up in parallel across a circuit and use it to measure volts, and then it's called a voltmeter. If you take a galvanometer and you cleverly switch the current direction every time it makes half a rotation, you can instead of just turning a dial when there's an electric current through it, you can make the dial go round and round and round, and this can drive a car, I guess, or something, and this is what's actually called an electric motor. That's how an electric motor works. You get continuous rotation. So the Earth itself is a huge magnet. There's a magnetic field, even just due to the nature of the Earth. Magnetic poles of the Earth are at the north and south poles. One's up in Canada, one's down in Antarctica. And it's due to electric currents, we think, inside the iron core of the Earth. And there's geological evidence that the Earth's magnetic field reverses direction, and has done so about 20 times in the last 5 million years. So out in space, there's many charged particles moving along, and that can be hazardous to astronauts. It's a form of radiation. But these cosmic rays are deflected away from Earth by the Earth's magnetic field. So this is partly protecting us from radiation. And these are the Van Allen radiation belts, where the radiation is trapped. we're down here safe on the surface of the Earth. So storms in the sun can hurl a lot of these cosmic rays or charged particles towards the Earth, and they can get trapped in the Van Allen radiation belts, and sometimes they even dip down into the Earth's atmosphere and glow. And that's called aurora borealis, or if it's in the northern hemisphere, or aurora australis, it's in the southern hemisphere.